Is Spectre the worst security vulnerability ever? I think so, and I'm going to explain how it works in this video to make my case, and I'm going to do it in just over 5 minutes. Let's get started. To understand Spectre, we first have to understand a little bit about how microprocessor works. On the left, I have a very simple program that simply adds together two variables x and y. In order to execute this program, the processor has to do four basic things. First, it has to load the value of x from main memory into the processor, here into a register called R1. Same thing happens for y, but into a register called R2. The processor then adds these two values together and stores the result in R1. And now we have to simply store R1 back to main memory, and we've completed our program. Now, this looks great, everything matches with our intuition, but under the covers things are not as simple as this seems because the processor is really fast, but main memory is slow, and I mean really slow, over 100 times slower than the processor. In order to hide this discrepancy between the speed of the processor and main memory, processor designers add a number of features. One of the features that processor designers add are called caches. The other feature is called speculation, and Spectre uses these two processor features in combination to leak secret data to people who aren't supposed to have it. So let's go over caches first. What a cache is a small memory that's inside the processor that's much faster than main memory that can be used to store frequently used values. So in this example, before we load x in a register R1, it gets loaded into the cache. Same goes for y. The processor then, just like before, adds the two results together and stores the result back into the cache. And this is where we gain the benefit of the cache. Because x was in the cache, we no longer have to write to the slow main memory. But notice that this creates an observable distinction in accesses to x and y, which are in the cache, and other data, which is not in the cache. And it's this difference in access speed that Spectre exploits to extract data that you're not supposed to be able to see. So now let's look at how Spectre itself works. So Spectre exploits this timing behavior of the cache in combination with speculative execution. So let's consider the program on the left where all we're doing is we're going to load a value from an array, ARR, R in this case, with an index that's too large. That index is called big. We're going to overflow the array, in other words. We're going to access well past the bounds of the array into data that we're not supposed to be allowed to see. Now normally this check would be guarded by the if statement above. If the index is too large, in this case bigger than the array size, then go to the failure mode. In JavaScript, for example, this will throw an out of bounds exception. The problem is that the processor, in order to hide some of the latency of main memory, is going to run ahead of where it knows the program ought to be in the hopes that it's going to do some useful work while waiting for some other slow main memory accesses. So in this case, the processor might guess that big is in fact smaller than array size, and then it's going to try and load that array access, that overflow array access, out of bounds array access, into register R1. It's then going to try and load the probe array value that corresponds to this out of bounds value that we just read. The processor will eventually recognize it made a mistake. It will throw away the values of R1 and R2 and roll back the state to before the processor made a mistake and restart program execution correctly. The problem is that this probe value was held in the cache even though it was loaded only speculatively. So now we can just measure the amount of time it takes to access every single element of the probe array. And when we do that, what we'll find is that when I is equal to the value of that out-of-bounds access array of big, we get a really fast access. When we try to access any other part of the array, we get a really slow access. And that means we can deduce the value of that out-of-bounds access very precisely. And that's it. That's Spectre in a nutshell. So why is Spectre the worst security vulnerability ever? Well, here are a few reasons. First, it's remotely exploitable. All you have to do is visit a website that contains the Spectre code, and you're going to start leaking sensitive information from your browser. What might that data be? Well, it could be stored passwords or cookies that authenticate you to Facebook, LinkedIn, other social media, or maybe even your bank. That's pretty bad. To make matters worse, this is not a software vulnerability. It's a hardware bug. There's nothing wrong with the software that's being exploited. and there's no good software workarounds either. Intel's released a microcode patch for their processors to reduce exposure to the bug, but it doesn't eliminate it entirely. Now, this bug relies on caching and speculation as the primary means to exfiltrate data. And the problem is that these features have been in most processors that are used in performance-sensitive systems, things like your laptop or servers in the cloud, or even recent smartphones. That means there are billions of these vulnerable processors out in the marketplace, and they're not all going to get replaced at once. And finally, the final nail in the coffin for this being the worst security vulnerability ever is that it's not even clear to me that there's a good hardware fix that's possible without eliminating speculation entirely. But given the discrepancies in speeds between the processor and the memory, there would be a huge performance penalty if we were to eliminate speculation altogether, or eliminate caching for that matter. I don't believe either of those things is going to happen. And so until some smart folks come up with a good workaround or a good mitigation strategy, it's not even clear that the bug can be fixed at all. If you found this video useful, make sure you click the like button and share it with your friends. If you found it a little bit too fast-paced to understand all the concepts, please subscribe to our YouTube channel. If there's enough demand, I'll make a longer, more detailed video that explains these things more carefully. You can also check out our earlier video on Meltdown, where I discuss caching, the Flush+Reload attack, and speculation, things that the variant of Spectre that I presented in this video share in common with the Meltdown attack that was released at the same time.